Welcome to the course for today. Today we're going to continue talking about shared state concurrency. And so last time we started talking about locks, and I started talking about tuple spaces. So today we're going to finish tuple spaces. I'm going to explain tuple spaces. It was a little bit fast last time. And then I'll talk about monitors, which are what's used in Java. And then finally, if we have time, I will start the presentation of transactions. So let me start by going to the slides. So last time we started talking about tuple spaces, but it was very fast, so maybe it was kind of hard to understand. So let me present now tuple space, which is a really interesting concept that's in between shared state and message passing, and it's actually used today. So a tuple space is a multiset, so it's like a bag, a multiset sometimes called a bag, and in there's tuples, and the tuples can be the same. So the same tuple can go in there more than once. So that's why it's a multiset and not a set. So a multiset, which is sometimes also called a bag. So there are three operations. You add a tuple with the write operation. You can remove a tuple with read, but this is actually synchronizing. So the remove is already doing synchronizing. It's going to wait until the tuple space has a tuple of the right form. So originally this was pattern matching, but in the implementation I will show you today, we are waiting for a tuple with a given label to appear in the tuple space, and we take one of them out. And then there's a non-blocking version of the read, which does not wait, but returns immediately with a Boolean, true or false. True if it has a tuple, and false if there's no such tuple. So tuple space for history was invented in 1985 by a computer scientist named David Gelernter, and he called his concept Linda. So sometimes this is called Linda, and his tuple space used pattern matching to remove a tuple. So we're going to only wait for the label. So it's slightly less general, but still giving the tuple space idea. So this whole idea is sometimes called coordination model. So when people talk about coordination models, they mean tuple spaces. And a language with a tuple space is sometimes called coordination language. And today there are very common systems called publish-subscribe systems, where you can publish messages and you can subscribe and get messages. So these are actually tuple spaces. They're example of coordination models. They're variation on coordination model. So a tuple space is actually a combination of shared state and message passing. It's very interesting because it has parts of both of them. So let me explain. So like a shared state, it's shared. So different threads access the tuple space and do read and write. So this is kind of like a shared data, okay? So it's easier than regular kind of shared state because the write and read are already large atomic actions. Putting a big tuple in the space is one atomic operation. Reading is removing a tuple. It's also an atomic operation. So they're already large atomic actions, so there makes it easy to program. So that's why it's like shared state. It's also like message passing, because you can think of the tuples as being sent and received. So a write is like sending a tuple, and a read is like receiving. And the difference between regular message passing is that you do not know the receiver. So when the thread does a write, it's like a send, but the thread does not know who is going to take the tuple out. So it's like doing a send where the receiver is not known. Somebody is going to receive it, but we don't know who. So that's the difference with message passing. The sender does not know the receiver. So why is that interesting? Well, here's an example. Let's say you have a set of printers and you want to send print tasks to the printer. So I want to print something, but I do not care which printer is printing. So that means I can send the print task to the printer pool, and one of the printers will take the task and print. But I don't care which printer. So this is like a send where I don't care who is the destination. Okay, so you can see how it's like message passing. So it's a send where you don't know the receiver, and it's like shared state because you have a shared tuple space. So you see it's kind of a concept that's sitting in between the two. Let me show you an example of something that we implement with tuple spaces. Remember, we used our concurrent queue with insert and delete, and we implemented with locks, we implemented with exchange, but we can also implement with tuple space. And I can show you the difference so you can see why it looks different. So the tuple space will use a read to put an element in the queue, and to remove, and a write for putting element in, and a read for taking element out. But it does not need the lock. So that's a really interesting difference with what we did before. It does not need a lock because tuples are unique entities, like tokens. You put a tuple in, and there is one more tuple. You take a tuple out, there is one less tuple. So taking a tuple is already like taking a token. So you don't need to do locking because implicitly taking the tuple is already giving you exclusive access to that tuple. It's a token. It's like a token. So that's why it's actually a little bit simpler. And so we have seen then 3 implementations of the queue. Let me show you the implementation with tuple space. So here's the queue with the tuple space. So we have our new queue operation. We have insert and we have delete. Notice the insert is doing a read and a write, and the delete is doing read and write. So the tuple space has one tuple which represents the state of the queue. Queue state. So the read will take the tuple state out of the tuple space, and then the write will put the new tuple state in there. And because it's a token, when the insert takes the tuple out, if you try to do another insert, the second one will wait. The second read will wait because the state of the queue is actually also a token. It's also a token, which means it has a unique identity and there's only one in the system. So if you take it, you have it, nobody else can have it. So you see the delete is also removing the tuple state with a read and then putting the new state in with a write. So let me go quickly back to the implementation with locks. So I'm going to go back to an earlier slide. So here is the queue implementation with locks, if you remember. So here we have a lock, then we read the cell, and here we write the cell. So we have a read and we have a write. But these are not tokens. If you read the cell, somebody else can also read the cell. So reading the cell is not giving you an exclusive access. It's not a token. If you want exclusive, you need the lock, which gives you the token. It's inside the lock. Okay? So the queue with locks, it's not enough to do read and write. You actually need the locks. Whereas if I go forward again now to the tuple space implementation, you can see that we don't need locks here because the read taking the tuple is already giving exclusive access because a tuple is a unique entity. If you remove it, it disappears from the tuple space and you are the only one with access to it. So a tuple is already like a token. Okay, so let me go to the chat now. So is that clear? It was a little bit quick last time. So maybe now I hope tuples, that it's actually clear how the tuples work. Okay, so let me actually show you how to make it work. So here I've actually have an implementation of tuples. I'm going to talk very briefly about the tuple implementation. So here we have a tuple space that we're going to implement. So we're going to implement the tuple space. We're going to use a queue. Internally, the tuples are stored in a queue. So we need a queue to implement a tuple space. So let me implement this. Implementation of tuple space. So let me put the queue in here first. And I compile that. And now I will put the actual tuple space. And then I'll explain a little bit how it works. So it's actually implemented as a class. You can see here. So here's the actual tuple space class. Okay, sorry, let me select it. Like this. And then we can actually create tuple spaces. So we can do something like declare ts is equal to new tuple space. Oh, I'm sorry. I'm sorry. Oh, I'm an idiot. I did it too fast. Let me go to the... Okay. So now you should see the screenshot. Sorry about that. So here I'm going to implement the tuple space. So I have the queue. I have the actual tuple space, which is a class. And now I can actually create a tuple space. And then we can use the tuple space. So if we put tuples in, they're like tokens. So if we do t write foo abc, this is a tuple. If we now do local t in ts read, I get a tuple of label foo, and I browse it. Then I will see the tuple appear here in the browse. But now you can also do synchronization. So let me do another one. Let me read a tuple which does not exist. Bar does not exist. Browse t, and so if I run this, nothing is displayed. You see, yeah? Nothing is displayed because the read operation is waiting. It's waiting because the tuple is like a token. So if I do ts write, and then I put in a tuple bar, then the read will continue. So you can see, for example, in the printer application, the printer can do a read, and it waits until somebody sends a print task. So the printer is always waiting for the task. Okay? So let me say a few words about the... So is that clear? So let me say a few words about the tuple implementation. Let me go back to the slides. So let's say a little bit how tuple space are implemented. So we need three things. Internally, it has a lock. We can't get rid of the lock, but now it's inside the tuple space. We have another data structure called a dictionary, and we have a concurrent queue. So we need three things to implement tuple space. So you see, it's actually very interesting. We can do a queue with the tuple space, but the tuple space also needs a queue. So queues and tuple space are actually kind of similar things. So the tuple space adds an extra thing, which is called a dictionary. So a dictionary is a kind of hash table. So it has pairs, key value pairs in there. So for example, it has a pair A, and then some tuple, and then B, some tuple. So it has a set of pairs stored in there, and you can index, you can look it up. You can say, does there exist a key of A in the dictionary? Does it exist key B? So you can add, remove, and test whether they exist. And the interesting thing is that it is in constant time, and also it's efficient space. So that means if you add elements to the dictionary, it will grow in size. It will allocate more memory as needed, but as much as you want until the system is exhausted. If you remove elements, then the dictionary will shrink in size. So it's not a fixed size array. It's a dynamic hash table. So it's a very efficient data structure, and it's implemented to give you constant time access. So dictionary is actually a very useful data structure that's often used. So the dictionary here on the right, each key, which is actually going to be the label of a tuple, and each key, the value is actually going to be a queue of tuples with that label. So this gives you the efficient access. If I want a tuple with label foo, I look at the key foo in the dictionary and I immediately get the queue for that tuples. So I'm using queues so that tuples, when they go in the dictionary, they come out in a fair way. So using a queue means that older tuples will be removed first. The tuples can come in, and I put them in the dictionary, and the one that was put in first comes out first. So that's how to implement the tuple space. So let me conclude. This is the end of the lecture on locks. So let me conclude. So we're talking about shared state concurrency. Remember, number of interleavings is exponential. We're building large atomic actions. So what I showed you so far is locks and tuple spaces. And the next two things I want to talk about are monitors and transactions, because locks and tuple spaces are limited in some ways, which I will explain, and we need to extend them to make monitors and transactions. So let me go to the chat. So is that clear? So we've talked now about locks, and tuple space is like a lock. I mean, a tuple, because a tuple is a token, but it's also like message passing. So it's an interesting combination, and it's used today in publish subscribe systems. But now locks are not enough. So now we're going to go to another concept, which is called monitors. And monitors are kind of a dinosaur, because Java is using monitors still. So many applications use monitors, but they're actually kind of problematic. They were invented a long time ago, but they have some problems. So I will now show you the monitors, and you'll see. Let me go to the slides, and we'll talk about monitors. So monitors. So a monitor is a lock, okay? But it's an extension of the lock. So it's a lock plus something else. And the reason is that a lock by itself is not enough. And let me say why. Consider, for example, it's true for many data abstractions, but consider a simple one called a bounded buffer. So a bounded buffer is like a queue, but it has a fixed maximum size. I can put elements in the buffer until it's full. But when it's full, I cannot put more elements. And I can remove elements from the buffer. Eventually it becomes empty. But when it's empty, I cannot remove any more. So there is blocking going on when it's full and when it's empty. So we cannot do it with a lock. It's not enough. We cannot implement a buffer with a lock. For example, what happens if a thread wants to put an element in the buffer and the buffer is full? Well, the thread has to wait, okay? But locks, they don't do that. Locks, they manage access to critical section. As long as there's only one thread inside, this is the buffer code, it runs. So a lock will not make a thread wait when the buffer is full. It only manages the the exclusive access. And the same happens if you want to remove an element from an empty buffer. Well, you have to wait until another thread puts an element in the buffer. So there has to be a way for threads to wait. So locks are not enough for this. We need locks, but we need something more. We need a way for the thread to wait until the buffer is either not full, so you can put more elements, or not empty, so you can take elements out. So this is a quite old concept. Like many concepts in computer science, they were first invented by Per Brink Hansen in 1972, and the modern version of monitors were developed by CAR, so Tony Hoare, in 1974. So you see they're quite old concepts, but they're still widely used today. In Java, synchronized objects are monitors, as we will see. So let me explain how a monitor works. So let me first give intuition on the monitors. So the monitor will add two operations to the lock called wait and notify, and it adds one data structure inside. Internally to the monitor, there's a data structure called the wait set. So the wait set consists of suspended threads. So if a thread does something with the monitor, it could go into the wait set, and there it waits. Okay? So the way the wait set is managed is by the wait and notify operations. So notify is sometimes called signal. This is actually means exactly the same. It depends on the text you're reading. If they talk about signal, you can say it's exactly like notify. So wait and notify are used to manage how threads go in and out of the wait set. So the wait will put a thread in, and the notify will take a thread out. So another point is the wait and notify operations, you cannot run them anywhere. You can only run them when you're inside the lock. So there are things, everything happens inside the lock. Okay? So the wait operation, okay, when a thread calls wait, it is put in the wait set. So the wait is very simple. You call wait and you are put in the wait set. And you release the lock. The wait is done inside. You release the lock, you're in the wait set, and so some other thread can maybe come in and do things. The notify does the other thing. When a thread calls notify, it wakes up one thread in the wait set. That woken thread will try to get the lock, but it cannot yet because the thread that called the notify is still inside. So when the thread that called notify goes out, then the woken thread can come in the lock. Okay? So the woken thread tries to get the monitor lock again at the place where it stopped. Okay? So you can call wait anywhere inside the lock, and it's waited. You wait there, and when you wake up, you continue executing from that point. Okay? Let me now give more precise semantics for this. The semantics I give here are actually the Java semantics. So this is exactly how monitors work in Java. In other languages, there can be slight variations. For example, sometimes monitors have more than one wait set. You can wait on different conditions. In the buffer, you could have one wait set for waiting till it's not empty and another one for waiting till it's not full. But Java does not do it like that. In Java, the monitor, for making things simple, the monitor has one wait set. Okay? So a monitor in Java also is an extension of an object. So the monitor is attached to the object. In some languages, it's a separate concept. In Java, it's attached to objects. So the object will have a lock and a wait set added to it. And there are the three operations, wait, notify, and there's a third one called NotifyAll, which I'll explain. So the wait operation works exactly as follows. So when a thread does wait, first it suspends the current thread. it places the thread in the wait set, and then it releases the lock. Okay, so all of these things are done in the current thread, so nobody can interfere, and then the lock is released and other threads could enter. So the notify has exactly the following semantics. It only does something if the wait set is non-empty. If the wait set is empty, it is a no operation. It does nothing. So if the wait set is non-empty, it removes a thread, but an arbitrary thread. So it picks a thread. Which thread? Well, that depends on other things. So for example, if you want fairness, then you could implement the wait set as a queue. Maybe you want to give advantage to older threads if you use a queue. But in general, it could be a set, it could be an arbitrary thread. So you remove an arbitrary thread from the wait set, and this thread, you let it resume. It starts executing again. It's no longer suspended. You say now it can execute, and it starts execute at the point it was suspended. So where it called wait, at that point, it's like the call to wait returns. Okay, when a thread calls wait, it doesn't return. It's put in the wait set. When someone else does notify, it's like the wait call is returning. And then this woken thread, it tries to get the lock. So it does not have the lock when it's woken up. It's outside of the lock. It tries to get the lock just like any other thread. If there's another thread in the lock, then it just waits. Okay, so that's the semantics of a lock. Let me go quickly to the chat. So you see, it's kind of lots of things are going on, and so we have to see how to programming. So there's a question. It's a bit like semaphores in C. Actually, not quite. A semaphore is a more primitive concept. You can use semaphores to implement monitors, but monitors do more because it's a lock plus the wait set. The semaphore is only managing the synchronization part of the exclusion. So semaphore is an early concept. So in the 1970s, there were many variations invented. People were trying to invent the right way of doing it, so they invented semaphores. But usually now semaphores are replaced by locks and monitors. So there's another question. What happens if the notify is called, but the wait set is empty? Well, in that case, the notify is a no-op. It just does nothing. It's like doing nothing. Okay? That means that nobody is waiting, so we don't worry. It doesn't hurt because new threads, if a new thread comes in the lock, it just starts working. So the wait set consists of threads that are waiting for something, waiting for some condition. But if there's no such thread, we don't worry. Then it doesn't really matter. We do nothing. So there's another question. Okay, I may translate it into English. I don't understand the goal, because if a thread does a wait when the buffer is empty, when will it get the notify? Why? How will it know that the buffer is no longer empty? Okay, that's a good question. So the buffer is empty. The thread tries to remove. So there's a thread doing get operation. It tries to remove element. It sees the buffer is empty, and it will call wait. So now it's just sitting in the wait set. And now assume another thread does a put. Another thread will do a put operation, and after it does the put, it calls notify. So the other thread doing the put will not do a wait because the buffer is not full. Let's say it's not full, but it will do a notify. So whenever a thread does an operation, at the end of the operation, it will always do a notify to see whether there's another thread that can use what it did. Okay, so the thread that does a put does notify, and the thread in the wait set is woken up, and it gets the lock, and it sees, hey, there's an element, and it takes the element, and everything's fine. So there's like a communication between the two threads. The getting thread goes in the wait set, sits there. The putting thread will notify the one in the wake set, which wakes up. So it's a way of making threads work together. So there's another question. What happens when a buffer is full? This is a very good question. As it is defined, there's no way to know whether we're waiting to have a non-empty or a non-full buffer. That is completely right. So we have a single wait set. So a thread that is waiting, that is doing a get, and it's waiting for non-empty, it will go in the wait set. A thread that is waiting to do a put, waiting for non-full, will also go in the wait set. So we're using the wait set for both kinds of threads. So this can maybe give inefficiency. So for example, if I do a get on empty buffer, I will go in the wait set. If I do another get, I will also go in the wait set. Okay? And so now I have two threads in the wait set. If I do a put, okay, if I do a put now, I will do notify. So it will pick one of those threads arbitrarily, and it will go, the thread will then do the work. So this is, the wait set is being used for handling empty buffers, but the same wait set is used for full buffers. So assume buffer is full, and I do a put, then I will go in the wait set. So the wait set has two kinds of threads. There's the threads that are trying to do a put and the buffer is full, and the threads trying to do get and the buffer is empty. So we're using the wait set for both kinds of threads. So how do we know the difference? Well, the wait set does not know the difference, but when it wakes up a thread, then the thread can the thread will go into the lock, and then it will check. So a thread trying to do a put, if it's woken up, it will go into the lock, and it will check if there's room. If there's room in the buffer, it does it. If there's no room, it just goes to sleep again. So it's possible to have two kinds of threads waiting on put or waiting on get, and the notify maybe wakes up the wrong one. It makes up the wrong one. So the buffer is full, and a thread is woken up, which is trying to do a put. Well, it just goes to sleep again. Okay, so it's not a bug, but it might give some wasted work. Okay. So let me show you some code. Let me do an application with it, and then you'll see how it works. Okay, so let me show you some code here. So, okay, let me first talk about NotifyAll. So I mentioned that there's a third operation called NotifyAll. So usually the notify operation, it will resume arbitrary thread. So usually that's not what we want. Okay, unless you're very smart and you're managing your monitor as a super genius, you do not use the notify. So usually we use another operation called NotifyAll. NotifyAll is basically doing notify for all the threads in the wait set. They're all resumed. That's kind of funny. Yeah? Maybe there's 10 threads waiting in the wait set. NotifyAll will wake them all up, and they all try to get the lock. Well, only one of them will get the lock. It will do something, and then the others will eventually get the lock, one after the other. And maybe if they're all trying to do put, maybe there's 10 threads trying to do put, and then I do a get. So there's one available slot. Then one of the puts will be happy, and it will do the put. The 9 other ones will try, and they will go back to sleep again. So you see that there can be some wasted operations. But the advantage of NotifyAll is that the code is very much simpler, as we will see. Notify is a problem because we don't the arbitrary thread might not be the one we want. So notify all is usually, this is the operation we will do in practice. So if you want to use monitors and you will want to be very careful that there's no bug, then almost always you will do notify all, because you don't know which of the arbitrary threads is the right one. So the trick is to wake them all up, and they will all try to do, and the wrong ones will just go back to sleep, and the right one will do the operation. Okay, so one thread will get the lock, it will execute the monitor code. If it's the wrong set, it will be put back into the wait set. If it's the right thread, it will do the operation. Now this, of course, can be inefficient if there's many threads in the wait set, but usually that's a rare operation. If I have so many threads trying to use the buffer that the wait set is full of threads, then something's wrong. I have contention, okay? Then my application is starting to become overloaded. So usually in a normal operation, there will not be so many threads in the wait set, maybe 1 or 2, okay, but not 100. But it's possible for there to be many. It is possible, and the system will be correct, even though it might be slightly less efficient. Okay, so let me now show you an example application called bounded buffer, and you'll see how to program with monitor. So let me first define my bounded buffer. So a bounded buffer, it's like a queue, but it has a fixed maximum size. So it's like an array, and once it's full, it's full. So you can put elements in. So there's 3 operations. You can create a buffer of size n. So the size is an important parameter. You allocate this memory, fixed memory, for the buffer. So the important thing about a buffer is that it will never overflow your memory. It's very important if you want to manage the memory. So you create a buffer of size n, and then you have 2 possible operations. Put an element in the buffer and get an element out. So put x will put x in the buffer. Get x will remove an element and bind it to x. So the put will wait if the buffer is full, and the get will wait if the buffer is empty. Okay, so that's how the bounded buffer handles the concurrency. So that's the definition of the abstraction. So in the picture, I have a buffer with 6 elements in there, A, B, C, D, E, F. So if I do a get, the A will come out. So I can put another element in, G. This one has a size of 10. So there's 6 elements, so I can put in 4 more elements. So that's how it works. So now we're going to implement it. The way it's implemented, usually a very efficient implementation, is an array of size n, but we organize the array as a ring. Okay, that means we can keep going round and round and round. And the idea is that when we go beyond n plus 1, we start again at 0. And the way to do that is to take the index, and if it's outside the range 0 to n minus 1, we replace it by the value modulo n. So it's always between 0 and n plus 1, and n minus 1. So we can go round and round, we can increment, and so the buffer will be working like this. So the way then it works is that we have 2 pointers, a first pointer and a last pointer. So the first pointer is the head, is the element that we will take out. So here it's element A. And the last pointer is the first empty slot. So here there's an empty slot. So you can see that when we take an element out, we increment first, moves around. When we put an element in, we increment last. So first and last are moving around. They're like chasing each other round and round and round. And as long as the number of elements is less than n, then everything is fine. Because if the last eventually will, if there's too many elements, the last will go around and it will hit the first on the other side, okay? And then we're full and we cannot put in any more. So if the number of elements is bigger than n, or it's tries to become less than 0, then we block the operation. So the number of elements always has to be between 0 and n-1 inclusive. So you see, we can keep going round and round. There's no problem with managing the elements. So now we can implement this using the monitors. So let me go to the chat. So is it clear? Is it clear how the bounded buffer works? So you can see we're going to go round and round and round this circle, and if the buffer gets empty or full, we have to block. So that's why we need the monitor. Okay, so that's the data structure we're going to implement. This is actually a very nice way to do buffers, and real life buffers are usually done like this. Okay, so let me show you now implementation of this. Implementation. So let me show you first the implementation without the monitor. Let me just show you the code intuitively how we do it. So I'm going to implement it as an object, class buffer. So there's the buff, which is an array, first and last pointers, the n, which is the size, which is a constant, and I, which is actually the number of elements in the buffer, which is going from 0 to n-1. So it's going to first allocate an array. So Oz has these vectors. So all languages have vectors of fixed size. So we're going to allocate an array from 0 to n-1. The first and last are both equal to 0. So that means that there's no elements in there. So the last points to the first empty slot. But because first is pointing to the same place, it means there's 0 elements and the I is equal to 0. Okay, so that's the initialization. Then we have put and get method. So here's the put method. So the way the put method works, so let me show you the code here. We put the element x into the last. You see, in Oz we have to, when we access the content of an attribute, we always have to use the read operation. So we have to use access buffer, access last. It's never automatic. So we take the buffer array dot, so this indexes the last element and it's x. Then we increment last. Remember, we increment last modulo n, and the size is incremented. So it's quite straightforward. Okay. Now there's a prefix here. There's something that happens before. Somehow we're only allowed to do this if the buffer is not full. So we have to wait until I, the number of elements, is less than n. So I put it in dot 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 here, but we'll see how to do that. So that's what the monitor is going to do. Okay? And the get is doing the opposite thing. So the first pointer points to the element we remove. Then we increment the first pointer, just like last. They both are moving in the same direction. We do modulo n because it's a ring. And then we decrement the number of elements. And again, there's a prefix here. We have to wait until the buffer is non-empty. So this wait stuff is going to be done with the monitor. But the actual code here, you can see how it works. Okay? So is that clear? Let me go quickly to the chat. So it's clear how the buffer is working. Okay, so you can see how the buffer works. Now let me show you how the monitor is going to help us manage that when we call the buffer from multiple threads. Okay, so we're going to use a monitor abstraction. So let me show you the actual code. So there's no special syntax in Oz for monitors. So we define monitors as an abstraction. We have a function called new monitor, which creates a new monitor. The monitor is actually a record with 4 fields: lock, wait, notify, and notify all. So we have the 4 operations with the following syntax. The lock is just a lock, but without the special syntax. We give it the statement as higher order, and we have to use quotes because lock is a keyword in Oz, so that's the way to use it if it's already a keyword. Then we have wait, notify, and notify all. So you can see it's a lock plus 3 more operations. Okay, so we're going to add this now to the bounded buffer. So here's how we do it. So in the code, the complete version, we add another attribute, which is the monitor. We initialize the monitor to a new monitor, and now we will update the put code. So all the red stuff is the new code that we add to make the monitor work. So first of all, there's the lock. So we can see that the whole thing here is locked, is exclusive access. And then we're inside the lock. And when we start, we check, is I greater or equal than n? If it is, that means the buffer is full. I is the number of elements. Okay? And if it is true, then we call wait. You can see the access m gives you the monitor record, the dot wait gives you the wait operation, and it's a 0 argument procedure, so we call it here. And once some other thread wakes me up, I will return. So the wait operation will eventually return when somebody else notifies me, and then I can try again. And the way to try again is to do a recursive. It's to try completely doing the put again. So then I can try again doing the put. Note that when you leave the wait, you do not have the lock anymore. You're outside of the lock here, right? When you're leaving the wait, the thread leaving the wait does not have the lock anymore. Okay, so it has to get the lock again. So the correct way to do this is to try again doing a put. This is kind of subtle. You cannot immediately run this code. That doesn't work. We will see why not. You have to try again doing the put. And maybe you're out of luck. Maybe some other thread gets in the lock before you and already does the put, and you go back to sleep again. Sorry, you have to wait until the next time. Okay? So you try again when you wake up, but there's no guarantee. You will probably get it, but there's no guarantee. If there's another thread, you might get it. Okay? This is the correct way to do. You can see it's actually not so simple. If you want to do naively, there's another way you can try. Maybe I just want to do like this. Okay? Maybe I just wait, and otherwise, and if I return, I immediately get the lock and do the code. This is incorrect. This is buggy. This code on this slide is incorrect. So you can actually find a scenario of the scheduler that makes it go wrong. And the reason why it's incorrect is because when you exit the wait, you have to go into the lock again. But there's no guarantee that you're the first one in. Some other thread might go in before you, and that other thread will take the slot that you wanted. So when you go in, maybe the buffer is full, and then it's a bug. Doing a put in a full buffer is a bug. So this code is buggy. Okay, so if you want to do correct monitor code, you actually have to try again completely. So you actually have to do a recursive try of a put again, because there's no guarantee that when you wake up after the wait that you will have the slot. Maybe some other thread will pick it from you. Okay, so let me go a sec back to the so this is one of the reasons why monitor is kind of complicated. It's because you have to worry about getting the lock that you're never the only one. There might be other threads. Okay, so is that okay? So this is actually important. Okay, so this is actually important, that when you wake up from a wait, you have to try again the whole method. You can't just start running the code in the method. You have to try again completely. Okay? Okay, so let me actually show some code now for this. This time I go to the screen. So here's the code for the tuple. Let me make some room here. So I actually have a piece of code here that implements the monitor. So the monitor also uses a queue for the weight set. Let me copy it in. So this is the code implementing the monitor. So first there's a queue. So this queue is used to implement the weight set. So let me do it first. You see, the notion of a queue is very important. Huh? And here's the actual monitor. So this is actually a procedure returning the different operations of the monitor. And then we have the bounded buffer. So let me show now a bounded buffer. So I'm not going to type it all in. So here's a correct version of the bounded buffer. So I think I have compiled it. Yes. So here is the bounded buffer. You can see here, this is a slightly different version. We have one attribute for each of the monitor operations. Here we call new monitor, which is a procedure with 4 results, and it returns these 4 guys. And then here we have the put operation, the correct version. So it does a lock. It waits until the buffer is not full. So if I is equal to n, you see it's slightly different. So if the buffer is full, then we wait. And after that, we have to try again to do a put, because the condition might become false, because another thread might get in before me into the lock and do already the put, so it's full again. Okay, so I have to try again completely. And then this is correct bounded buffer. Okay, so we can compile this, and then we can actually execute the bounded buffer. So we can say declare bounded buffer is equal to new, let me see, what is the name of it's called buffer, new buffer size, let me make a small one, size 3, so we can actually make it full. So we can put elements in there now. So we can say, for example, bb put a. So the a goes in there, and then we can do something like bb get x browse x, and the a comes back out. Okay, but we can also make the buffer go full. You put a in there, put b in there, put C in there, put D in there, browse, done. So here I'm putting 4 elements into the buffer, but the buffer only has size 3, so nothing is displayed here. But if I remove one element, get X, browse X, so I put A in the buffer, then I put B in the buffer, C, and I'm trying to put D, but it doesn't work because the buffer is full. So I'm blocking here. But if I remove the element here, then the D will be able to get in. So what will be displayed here? So I put A in the buffer, and then B, and then C, and then D. So the first element coming out is going to be what? It's going to be A, of course. So A, and then it's done. Then you can see the buffer was able to put in the D, okay? And now I can keep taking elements out. I remove B, I remove C, I remove D. Now if I do again a get, now the buffer is empty, I will display nothing. But if I do put E in there, then the get is waiting. You can see it's actually waiting here. If I put an E in there, then the waiting get will display. So you can see the buffer is actually coordinating the work between the different threads. Okay, so you see how it works? So of course I'm going to put the code on the Moodle. Question, so there's a question. Should we do a notify after adding the element? Yes. And in fact, the right way to do it is to do a notify all. So you are correct. I actually have a bug in the code there. Thank you for noticing that. So if you look at the, let me show you here. Let me go back to the screenshot. If you look at the buffer element, notify, notice that I'm actually doing notify here. So you always have to start with a wait and end with a notify. So I think you are right. I think there's actually a bug in my slide, which I will fix. Thank you. So let me go to the slide again. Very good. I'm always very happy when people are paying attention. Helping me debug everything. So I made these slides very recently, so they're still bugged. So as correctly pointed out, there should actually be notify here. So there should actually be a notify in here. Okay. Notify all. We actually have to do notify all here. And in fact, there's a programming pattern. So if you look at this code here, you can see we have a condition, we have a wait, and at the end we have a notify all. So it's kind of a general pattern. So when you program with monitors, you have to do it like this always. Unless you are a super expert, you always do like this. You have the condition here to see whether you allowed to do it. If it's I keep making mistakes here, so there has to be a wait here. Okay, so I will fix the slides. Don't worry when I put a fixed version on the Moodle. So the idea is that if the condition is not true, so if we're not allowed, if we try to put in a put and we don't have any elements, so if the buffer is full, we have to do a wait and then we try again. Otherwise, we do the thing and at the end we do notify. So this is kind of a programming pattern. There's another way to write this using a while, which is maybe a little bit shorter. Okay. The while loop. And the while loop, you have to be a little bit careful here. So let's say I want to do put, but buffer is full. I wait. When I wake up again, the while loop will test the condition again. You see? The while loop, when the wait wakes up, it will go immediately to the while and it will test the condition again. And the thing is, it might become false because another thread might come in before me. So it's not enough to do an if. You have to do a while, or you have to do recursion like this. You have to try again, or you have to test the condition again. Otherwise, you might be a bug. Otherwise, another thread might fill the buffer, and then you try to put, and the buffer is full. So it has to be a while loop or a recursive call here. So this is the programming pattern for monitors. If you don't do like this, then it's going to be buggy. Okay. So in Oz, we will use recursion because funnily, strangely, Oz does not have while loops. Kind of a weird omission. But in a language like Java, you will do while loops. Okay. So that's the monitor pattern. So when you program with monitors, then the recommendation is to always do like this, using wait, using NotifyAll, and using a while loop for the condition. Okay? If you do that, then it will be correct. But if you use an if, it will be wrong. Okay? Let me go a little bit back to the question. So there's a question. The while loop does not recall the lock multiple threads. So we're assuming when you exit from a while, from the wait, that you will try to get the lock again. Okay, you're assuming that when you come in, you're always trying to get. So when you somehow go into the code of a lock, that implicitly you are trying to get the lock again. And that's how, for example, Java will do it. Okay, so you're assuming that there's no way really to wake up from a while and immediately go in there, that you will automatically try to get the lock again. Okay, and we'll see how it works when we do the implementation of monitors. So I'm going to make a small break, but then we will show the implementation, and you'll see that when you wake up from a while, you actually try to get the lock again.